Welcome to the first microconference session this day with safe systems with Linux. I start this with a short intro on this and give some aspects of dependable Linux systems. I will get support by Kate and sometime for one or two of the things I want to share. So it's about setting the theme, and yeah, when you think like, what about Linux safety critical part, which basically means like risk potentially to human life and other things. It's not so the security topic alone, it's really about functional safety. And we see that this is actually being used in safety critical systems today. So we see the examples of automotive where you bring it in. Sometimes it's hidden, not everybody's just making a lot of noise around it. And it's also went to space, it's used in satellites, other parts, and you find it also in a lot of industry, robotics, and so on. So it's nothing which is new. And that's basically it. But for many, maybe the definition of functional safety is new. And basically, in the definition of safety, it's the freedom from unacceptable risk. It means that there is still a residual risk which you cannot avoid, but you try to lower as much as possible. Typically, try also to say like, it could be a risk to the human, but if it would be a normal scenario, the risk must not be higher. So if you automate something, you change something, it should not be a higher risk than the person would have when he would be alone or see. So, and it's about health of people, directly, indirectly, because of damage. And the functional safety is then the part of the safety that depends on the system, requirements, operating correctly, and responding to the properly to the inputs. So that's the overall environment on this. And therefore, in functional safety, you expect that the software does behave as specified, which means like you have an understanding on what the software is. And we know that, well, we have sometimes the code as specification, and it could be sometimes good to just rephrase to come into points where you would say, here's something more needed, or do I have any evidence on testing something, verify that the code does what it should, and how do I make a connection? How do I trace that this is not changing over time? And yeah, then also how is the interference with other parts that you really know, like, well, simple example, your GPU is heating up, so your CPU is decreasing the frequency to just overcome the terminal things, and suddenly your system behaves slower while just doing more. So these are things, and think about all these events, what could happen. And for this, in industry, there are many, many different standards for automotive, medical, aerospace, space, and some other standards are there. It's like best practice developed over 50 years in industry. So it basically writes down what they have done, but maybe not for as complex systems as Linux is supposed to be, right? If you see original standards may think about 5 to 10K lines of code, which is nothing if you see the size of the Linux kernel. But all these standards still share a lot of similar best practices and demands. And it also shows that you need to know every part of your system and also the environment around it, so left and right, what's next to your core part of interest, maybe the Linux kernel as we are here. And therefore you do a lot of things about the requirements work, expectations, the testing, then writing the documentation around it that others know and can follow things and get the things traced together. And a few considerations.
So the key thing that was an insight for me anyhow is safety has to be thought of as part of a system. What we're trying to do is there's various needs that a system is trying to fulfill, and this maps into the requirements on the components into the system. And so those standards that Philipp was referring to earlier all have assumed this type of model underneath them. And so our challenge becomes, and when you go to the next slide, open source components do not speak that language, okay? And so the question here is, how can we use these open source components, things like the Linux kernel, in a system and be able to do the right level of analysis in order to satisfy the argumentation and convince ourselves it's safe to use, okay? Or convince whoever's making this product that the risk is low enough that you can use it. The Linux kernel, has processes, it has quality, it's been there for forever. But in some of what we're seeing is we are seeing company after company after company trying to sort of work their way around things and not collaborate on bringing a common expectation into play. Okay, everyone's doing, like I say, I talked to a company here in Europe, and they've taken a Linux kernel through 61508 already, but it took them 6 years. And none of that stuff's upstream, okay? So everyone is going off and redoing it, and we really need to start collaborating on how we can actually get the information in a way that when someone figures it out, we can share it. That is what we're trying to go towards. How we do this sharing is an open question. Chuck was talking about some of the aspects we're looking at and exploring right now, and there'll be more discussions today. If you want to move on, go for it if you want.
Yeah, so there are a set of challenges with safe usage in the Linux kernel. The interesting thing is we already have a lot of things there. So each patch that comes and is submitted to the Linux kernel has a reason. It could be a feature extension, it could be a bug, sometimes the bug is the feature. And you may even say like, okay, here, right, where you also just submit something, say, this is behaving wrong, but actually you return, say, no, it's not behaving wrong, it's what I meant to do, so it's not supposed to do these kind of things. So this shows us already something about what things are required and what not. And it's a lot about the what and the why. You see the iterations of the different kernel version, or like you have the V2 patch, V3, something like this. So there you can also see that there is something there, and it's a form of a requirement, an expectation, something you have in there. And then if you, you test it most likely, you will check it locally, you verify, so you basically fulfill all these kind of things also safety standards are doing, but it's not in such a way, it's very structured, but it's not in a such structured documentation way that you will have an easy way of access later on, that you can recheck this again. And this is not so, it is to a certain set systematically and still not completely systematically, and that's why we also come together here. Yeah. Right, and this is like this morning where we have a lot of different ideas on this. And I think the nice thing, as we talked about the system and the practical use, so Igor will start off with the practical qualification efforts which NVIDIA took. So this is something as a starting, setting us into the theme, then pointing to the program verification part to look into much more formal things. Also, how could we define specification, formal specification, improve the documentation within the kernel, and then bring things forward. Exactly. Thanks, Kate, for finishing off that. We stick in the time. And at the end, it's system engineering, as Kate said. So it's really like understanding how you use Linux, what part of the kernel, and so on. And by this, I think we don't, especially the intro, we just move on to get to Igor. I'll already bring up your slides.
And hopefully, I saw Brian's hand go up during this, but hopefully we can catch up on the questions and in the break or in discussion in the hallway as well, or feel free to bring it up if it comes up again, okay? Thanks.